Hello, everybody, and welcome to this live stream. I am the Shy Hat, and we're going to be doing our Advent of Cyber 2023 daily challenge today. Today is day 16. If you want to join in with the daily challenges for today's this year's Advent of Cyber event hosted at TryHackMe.com, you'll want to go to this particular link right here that I'm leaving in the chat. All right, so let's get to solving today's beginners friendly cybersecurity challenge. All right, so today we're doing day 3 of machine learning. So we've spent the last 2 days learning about machine learning, and I think this might be the capstone, the final day of machine learning here at the Advent of Cyber event. So let's take a look at what's going on. So McCready has locked McSkitty out of his ELF HQ admin panel by changing the password. To make it harder for McSkitty to perform a hackback, McCready has altered the admin panel login so that it uses a CAPTCHA to prevent automated attacks. A CAPTCHA is a small test, like providing the numbers and an image, that needs to be performed to ensure that you are human. This means McSkitty can't perform a brute force attack, or does it? After the great success of using machine learning to detect defective toys and phishing emails, McSkitty is looking to you to help him build a custom brute force script that will make use of ML to solve CAPTCHA and continue with brute force attacks. There is, however, a bit of an irony in having a machine solve a challenge specifically designed to tell humans apart from computers. All right, so what are today's learning objectives? So today's learning objectives are to learn about complex neural network structures, to learn about how a convolutional neural network functions, learn about using neural networks for optical character recognition, and to learn about integral neural networks in red team tooling. All right then. So for today's challenge, to access the machine, we do need to start a VM today, and there is split screen available. Okay, so what we need to do at the top of the day 16 task, we're going to click on this button right here to start the virtual machine associated with today's task. And that's going to split the browser pane in the browser tab in two with 2 panes. So on the left-hand side is the Track Me webpage, and on the right-hand side is the virtual machine that we're going to be using to solve today's task. So let's go back up to the top over here so we can continue learning while the virtual machine over here is initializing. So let's talk about our introduction. So in today's task, we'll get our first look at how red teams can use ML to help them attack systems. But before we can start attacking the admin portal, we'll need to expand on some of the ML concepts taught in previous tasks. Let's dive in. Convolutional neural networks. In the previous task, we talked about neural network structures. However, most of these structures were fairly basic in nature. Today we will cover an interesting structure called a convolutional neural network, or CNN. CNNs are incredible ML structures that have the ability to extract features that can be used to train a neural network. In the previous task, we used the garbage in, garbage out principle to explain the importance of our inputs having good features. This ensures that the output from the neural network is accurate. But what if we could actually have the neural network select the important features itself? This is where CNN comes into play. In essence, CNNs are normal neural networks that simply have the feature extraction process as part of the network itself. This time, we're not just using maths, but combining it with linear algebra. Again, we won't dive too deep into the maths here to keep things simple. We can divide our CNN into 3 main components: feature extraction, fully connected layers, and classification. We've actually covered the last 2 components in the previous task as a simple neural network structure. So our main focus for today will be on feature extraction, on the feature extraction component. Okay, so everybody, see here that that our virtual machine has initialized. So what we can do is we can put this virtual machine in its own browser tab. We can do that with this button right here, which is View in Full Screen. So we can click on this button, which is located at the bottom here, and that'll let us access our virtual machine in full screen, which makes things a lot easier for us when we're trying to take a look at the terminal. And that makes it so that on the web page we can close out this this window pane right here by clicking on this button, which is labeled Exit Split View. Okay, and after we've done that, we have our full screen back on the web browser for the TryHackMe web page, and we also have a full screen for the virtual machine. All right, so back to the task at hand. So we're talking about feature extraction. CNNs are often used to classify images. While we can use them with almost any data type, images are the simplest for explaining how a CNN works. This is the CAPTCHA that we're trying to crack. So we see here there's a typical CAPTCHA over here, which has some numbers that a user would have to input to prove that they were able to read the image and pass the test. Since we'll be using a CNN to crack CAPTCHAs, let's use a single letter in the CAPTCHA as our image. So here the number 4 has been extracted out. So let's talk about image representation. The first question to answer is, how does a CNN actually perceive this image? The simplest way for a computer to perceive an image is a 2D array of pixels. Sorry about that. It's a 2D array of pixels. A pixel is the smallest area that can be measured in an image. Together, these pixels are what create the image. A pixel's value describes the color that you are seeing. There are two popular formats for pixel values. So there's the RGB value. The pixel is represented by 3 numbers from 0 to 255. These 3 numbers describe the intensity of the red, blue, and green colors of the pixel. And grayscale. The pixel is represented by a single number from 0 to 255. 0 means the pixel is fully black, and 255 means the pixel is fully white. Any value in between is a shade of gray. To represent the image as a 2D array, we start at the top left and capture the value of each pixel, working our way to the right in rows before moving down. Let's take a look at what this would look like for our CAPTCHA. So we see here that the image here is being increasingly pixelized so that we're able to map out the color of each one of these pixels. Now that we have our representation of the image, let's take a look at what the CNN will do with the image. All right, so this step is called convolution. There are 2 steps in the CNN feature extraction process that are performed as many times as needed. The first step is convolution. The maths are about to get slightly hectic here, so let's take a deep breath and dive in. During the convolution step of the CNN's feature extraction, we want to reduce the size of the input. Images often have several thousand pixels, and while we can train a neural network to consider all of these pixels, it will be incredibly slow without really adding any additional accuracy. Therefore, we will perform convolution to summarize the image. To do this, we move a kernel matrix across the entire image, calculating the summary. The kernel matrix is a smaller 2D array that tells us where in the image we are currently creating our summary. This kernel slides across the height and width of the image to create a summary image. Take a look at the animation below. So we see here that as we're panning across the image, we're getting an amalgamation of these different pixels, and it's mapping it to an array over here. As you can see from the animation, we start at the top left of our image looking at a smaller 3x3 section. We can calculate the summary by multiplying each pixel with the value in the kernel. These kernel values can be set differently for different feature extractions, and we're not limited to a single run. The values of these kernels are usually randomized at the start and then updated as the network is busy training. We say that each kernel run will create a summary slice. As you can see from the animation, by sliding this kernel across the entire image, we can create a smaller summarized slice of our image. There are a couple of reasons we want to do this. As mentioned before, we can create a neural network that takes each pixel as input, but this would be an incredibly large network without improved accuracy. The summary created by the convolution process allows us to capture the image's important details without needing all the pixels. If our CNN's accuracy decreases, then we can simply make the kernel smaller to capture more details during the input phase. The term used for this process is sparse interaction, as the final neural network won't directly interact with each pixel. If you would like to learn more, you can read about it here. If we calculate a feature in one location in our image, then that feature should be just as useful as a feature calculated in another location in the image. Making use of the same kernel to determine the summary slice means this condition is met. If we update the weights in one of our kernels, it will alter the summary for all pixels. This results in something called the property of equivariance to translation. Simply put, if we change the input in a specific way, the output will also get changed in that same way. If you want to learn more, you can read about it here. We perform this summary creation with several kernels to create several slices that are then sent to the next step of our CNN feature extraction process. The next concept is pooling. The second step performed in the CNN feature extraction process is pooling. Similar to convolution, the pooling step aims to further summarize the data using a statistical method. Let's take another look at our single slice and how a max pooling will provide a summary of the maximum values. Okay, so we see that this 16 by 16 set of information here is being summarized between these four quadrants right here, and then it is being summarized, I would suppose. As you can see again, for each kernel, we create a summary based on the statistical method. For max pooling, this is finding the maximum value in the pixels. We could also use a different statistical method, such as average pooling. This calculates the average value of the pixels. And that's basically it. That's how the CNN determines its own features. Depending on the network structure, this process of convolution and pooling can be repeated multiple times. In the end, we're left with the pooled values of each of our slices. These values now become the inputs for our neural network. Fully connected layers. Now that we have our features, the next stage is really very similar to the basic neural network structure that we used back in the Introduction to Machine Learning task. We'll create a simple neural network that takes inputs, the summary slices from our last pooling layer, run them from the hidden layers, and then finally provide an output. This is called the fully connected layers portion of the CNN, as this is the part of the neural network where each node is reconnected to all other nodes in the next layer. Classification. Lastly, we need to talk about the classification portion of the CNN. This is the output layer from the fully connected layers portion. In the previous tasks, our neural networks only had one output to determine whether or not a toy was defective, or whether or not an email was a phishing email. However, to crack CAPTCHAs, a simple binary output won't do, as we need the network to tell us what the character, and later the sequence of characters, is. Therefore, we'll need an output node for each potential character. Our CAPTCHA only contains numbers, not letters. So we need an output node for 0 to 9, totaling 10 output nodes. Having multiple output nodes creates a new interesting feature for our neural network. Instead of simply getting one answer now, all 26 outputs will have a decimal value between 0 and 1. We'll then summarize this by taking the highest value as the answer from the network. However, nothing is stopping us from reviewing the top 5 answers, for instance. This can help us identify areas where a neural network might be having issues. For example, there could be a little confusion between the characters of M and N, as they look fairly similar. Reviewing the output from the top 5 nodes will show us that this might be a problem. While we might not be able to solve this confusion directly, we could actually use this to our advantage and increase our brute force accuracy. We can do this by simply discarding the CAPTCHA if it has an M or N and requesting another one to avoid the problem entirely. Training our CNN. Now that we've covered the basics, let's take a look at what will be required to train and use our own CNN to crack the CAPTCHAs. Please note that the following steps have already been performed for you. The next steps will be performed in the hosting the model section. However, understanding how training works is an important aspect, so please follow along and attempt the commands given. We will be making use of the attention OCR for our CNN model. This CNN structure has a lot more going on, such as LSTMs and sliding windows, but we won't dive deeper in these steps in this instance. The only thing to note is that we have a sliding window which allows us to read one character at a time instead of having to solve the entire CAPTCHA in one go. We'll be making use of the same steps followed to create CAPTCHA 22, which is a Python pip package that can be used to host a CAPTCHA cracking server. If you're interested in understanding how this works, you can have a read here. While you can try to run all the software yourself, most of the ML components runs on a very specific version of TensorFlow. Therefore, making use of the VM attached to this task is recommended. In order to crack the CAPTCHAs, we will have to go through the following steps. 1. Gather CAPTCHAs so that we can create labeled data. 2. Label the CAPTCHAs to use in a supervised learning model. 3. Train our CAPTCHA cracking CNN. 4. Verify and test our CAPTCHA tracking CNN. 5. Export and host the trained model so we can feed it CAPTCHAs to solve. And 6. Create and execute a brute force script that will receive the CAPTCHA, pass it on to be solved, and then run the brute force attack. Steps 1 to 4 are quite taxing, so they have already been completed for you. We'll do a quick recap of what these steps involve before moving on to hosting the model and cracking some CAPTCHAs. To do this, you have to start the Docker container. In a terminal window, execute the following command. Alright, so now we can run some of these commands inside of our virtual machine. So let's copy this command that's going to run a Docker container. We can go to our virtual machine and then open up a terminal using this shortcut command or this one or this one. So I'm going to use this one. And in the terminal window that appears, I'm going to increase the size of the window so we can see better what's going on. Okay, and then we're going to paste in the command that we copied by using Control-Shift-V. So Control-Shift-V, okay, this is the Docker command that's going to run the Docker container, and we run that. Okay, so let's get more instructions from the web page. This will start a Docker container that has the TensorFlow and AOCR already installed for you. You will need to connect to this container for the next few steps. First, you need to find the container's ID using the following command. So let's use Docker PS to identify the ID number of the Docker container we created. Okay, so this is the ID number of the Docker container that we created. So we're going to keep note of that, and then we're going to use it for the next command. So we're going to, this command over here is going to connect to the container. So we're going to copy this, and then we're going to paste it in. Oh, let me try that again. So we're going to copy this, and then we're going to paste it in. But here in the container ID, we're going to delete this, and then we're going to copy our Docker container ID number. So we copy this, Control-C, Control-Shift-C, and then paste it, Control-Shift-V. Okay, and then we can run the command. So now, we're not working inside of the virtual machine, we're working inside the Docker container, which is running inside of the virtual machine. So we're 2 layers deep. Okay, so you can now navigate to the following directory for the next few steps. So we're going to the OCR directory. So let's move over to the OCR directory. And then we're going to gather training data. In order to train our CAPTCHA cracking CNN, we first have to create a data set that can be used for training. Let's take a look at the authentication portal for HQAdmin. Alright, so we're going to open this particular web page inside of the VM. So in our VM, we can just open up our Firefox web browser with this shortcut button right here. And it will conveniently take us to that exact web page, which is nice. So we see here that there's a basic login page with a field for username, password, and CAPTCHA. So we see here that there's a CAPTCHA with a bunch of numbers here, and we have to fill in the CAPTCHA, and then click sign in to sign in with all of the fields completed. All right. So as you can see, the authentication portal embeds a CAPTCHA image. We can get the raw image using a simple curl command from the normal terminal window. All right, so if we curl this down, we copy that, and then we will minimize this window, and then we will open up a new terminal window, and then we will paste in that command. All right, so we see that inside of the response, we get this very long base64 encoded version of the CAPTCHA image. So we know that we can receive the CAPTCHA image from by accessing the login page. All right, so I'm going to close out this terminal window. In the output, you'll see the base64 encoded version of the CAPTCHA image. We can write a script that will download this image and prompt us to provide the answer for the CAPTCHA to store in the training data set. This has already been done for you. You can view the stored data by using the following command in the Docker container. Okay, so we're going to run this command inside of our Docker container. And we can see all the different PNG files that have been downloaded and used as the training data set. Okay, so creating the training data set. Next, we will need to create the training data set in a format the AOCR can use. This requires us to create a simple text file that lists the path for each CAPTCHA and the correct answer. A script was used to create this text file and can be found under the labeling directory. You can use this command to view our text file that was created. Okay, so let's take a look at the text file that was created for the training data. Okay, so we see that it looks like inside the data set for each one in this directory, this labeled PNG, and this was the answer for the CAPTCHA, it looks like. All right. Once we have our text file, it can be converted into a TensorFlow record that can be used for training. This has already been done for you, but you can use the following command to create the data set. So we would use this command to create the data set. So we'll see that we're running into some errors inside here, but that's okay because this was just used as a example, and everything is already in place for us, so we don't really need to do that step to complete our tasks. As mentioned before, this has already been done for you and stored in the labels directory. We have created two data sets, one for training and one for testing. As mentioned in the Introduction to Machine Learning task, day 14, we need fresh data that our CNN has never seen before to test and verify that the model has been trained accurately, not overtrained. Just as in the previous tasks, we'll only use the training datasets to train the model, and then the testing dataset to test its accuracy. Training and testing the CNN. Finally, we can start training our model. This has already been done for you, but with all the preparation completed, you would be able to use this command to start the training. Okay? So let's try running this. Okay, so it looks like this is running. Training will now begin. Once the training has completed a couple of steps, stop it by pressing Ctrl-C. Let's take a look at one of the output lines from running the training. So let's stop this using Ctrl-C. So this particular line right here, in each of these steps, the CNN is trained on all of our all of our inputs. Similar to what is discussed in the Introduction to Machine Learning task, each image is given as an input to the CNN, which will then make a prediction on the numbers that are present in the CAPTCHA. We will then provide feedback to the CNN on how accurate its predictions are. This process is performed for each image in our training dataset to complete one step of the training. The output from the AOCR shows us how long it took to perform this particular round of training and provides feedback on the loss and perplexity values. Loss. Loss is the CNN's prediction error. The closer the value is to 0, the smaller our prediction value, our prediction error. If you were to start training from scratch, the loss value would be incredibly high for the first couple of rounds until the network is trained. Any loss value below 0.005 would show us that the network has either completed its learning process or has overtrained on the dataset. Perplexity. Perplexity refers to how uncertain the CNN is in its prediction. The closer the value is to 1, the more certain a CNN is that its prediction is correct. Consider how perplexed the CNN would be seeing the image for a first time. Seeing something new would be perplexing, but as the network becomes more familiar with these images, it's almost as if you can't show it anything new. Any value below 1.005 would be considered a trained or overtrained CNN. As a CNN has already been trained for you, you can now test the CNN by running this. Okay, so we run this. Testing will now begin. Once a couple of testing steps are complete, you can stop it once again, use Control-C, and take a look at 2 of the lines. As you can see from the testing time, running a single image sample through the CNN is significantly faster than training it on the entire dataset. This is one of the true advantages of neural networks. Once training has been completed, the network is usually quick to provide a prediction. As you can see from the predictions provided by the end of the lines, one of the CAPTCHA predictions was completely correct, whereas another was a prediction error, mistaking a 5 for a 6. If you compare the loss and perplexity values of the 2 samples, you will see that the CNN is uncertain about its answer. We can actually use this to our advantage when performing live predictions. We can create a discrepancy between CAPTCHA prediction accuracy and CAPTCHA submission accuracy simply by not submitting the CAPTCHAs that we were too uncertain about. Instead, we can request a new CAPTCHA. This enables us to change the OPSEC of our attack, as the logs won't show a significant amount of entries for incorrect CAPTCHA submissions. We could even take this step further and save the CAPTCHA images that were incorrect on submission. We can then label these manually and retrain our CNN to further improve its accuracy. This way, we can create a super CAPTCHA cracking engine. You can read more about this process here. Okay, so hosting our CNN model. Now that we've trained our CNN, we'll need to host the CNN model to send it CAPTCHAs through our brute forcing script. For this, we will use TensorFlow serving. Once the CNN has been trained, we can export the weights of the different nodes. This allows us to recreate the train network at any time. An export of the trained CNN has already been created for you under the OCR/model directory. We'll now export the model from our Docker container using the following command. Okay, so we need to export, copy this, and run this inside of our Docker container. Once that's complete, you can exit the Docker container terminal using the exit command, and then kill it using the following command. Okay, docker kill container ID. All right, so let's do that. We exit, and then we run docker kill. We're going to edit this command right here. So this command was retrieved using the up arrow on our keyboard, and that accesses command history. So we press the up arrow to bring up the command history, and then we edited that command so that we could include the Docker ID number right here. So we run the command, and that shuts down the Docker container. Okay, TensorFlow serving will be run in a Docker container. This container will then expose an API that we can use to interface with the hosted model to send it a CAPTCHA for prediction. You can start the serving container using the following command. So this command will start up our tensor serving Docker container. So we're going to copy that, and we're going to run that from the terminal. Okay, so we're just going to leave this alone and go to the next step. This will start a new hosting of the OCR model that was exported from the AOCR training docking container. We can connect it to the model through the API hosted on this particular web address. So what we can do is we can copy this address, and then we can go to our Firefox web browser. We can go to a new browser tab, and then paste in this address. So we see here that this is an API right here that is that we can use as part of our brute force attack. Okay, so now we're ready to help Expedia regain access to the HQ admin portal. All right, so we're talking about brute forcing the admin panel. We are now ready to for our brute force attack. You've been provided with the custom script that we will use. You can find the custom script and password list on the desktop in the brute forcer directory. Let's take a look at the script. Okay, so we have a Python script. We're importing a bunch of modules and libraries. We're getting a bunch of variables that we're going to be using for our web requests, our username or password. We have the website URL that we're brute forcing, and we have the model URL that we can pass CAPTCHA images for it to solve. Okay, and we have a passwords list that we're using, and then a bunch of other stuff. Let's take a look at what's going on down at the bottom. So number one, first we load the libraries that we'll be using. We'll mainly make use of the Python's request library to make web requests on our behalf. Number two, we will load in our password list that will be used for the brute force attacks. Number three, in a loop, we will perform our brute force attacks, which consists of the following steps. Number one, make a request to the HQ admin portal to get the cookie values and the CAPTCHA image. Number two, submit the CAPTCHA image to our hosted CNN model. Number three, determine if the prediction accuracy of the CNN model was high enough to submit the CAPTCHA attempt. Number four, submit a brute force request to the HQ admin portal with the username, password, and CAPTCHA attempt. Number five, read the response from the HQ admin portal to determine what to do next. All right, so let's run our brute force attack using the following command at the terminal window. Okay, so we're going to go to the brute force directory, and then we're going to run the brute force script with Python 3. Okay, so what we need to do is we need to start a new terminal window to do this. So we're going to click on this shortcut button to open up a new terminal window, and then we're going to make it nice and big. And then we're going to run the command. Okay, so we see here that the brute force attack is commencing. It's running through the username admin and the password as a bunch of these different ones. And occasionally, we are submitting incorrect CAPTCHA values. But eventually, we come across a valid username and password, which is this right here. So let it run for a minute or two, and you will regain access to the HQ admin portal. All right, so what is the conclusion for today's task? So, conclusion, in this task, we have shown how machine learning can be used for red teaming purposes. We have also demonstrated how we can run custom scripts to perform basic tasks, such as brute forcing the authentication of a web application. All we need is a spark of creativity. While we could have used a pre-trained model such as Tesseract OCR, it wouldn't have been nearly as accurate as one trained specifically for the task at hand. This is true for most ML applications. While generic models will work to some degree, it's often better to train a new model for the specific task we're handling. Now that we've had a taste of what's possible, the sky's the limit. All right, so let's finish off today's challenge by answering the questions below. Okay, so what key process of training a neural network is taken care of by using a CNN? That is the process of feature extraction. What is the name of the process used in the CNN to extract its features? Okay, in this case, it is called convolution. What is the name of the process used to reduce the features down? Okay, this was called pooling. What off-the-shelf CNN did we use to train a CAPTCHA cracking OCR model? Okay, if you remember, this was called attention OCR. what is the password that McCready set on the HQ admin portal? Okay, so if we go back to our machine, this was the password, and we can copy this with Control-Shift-C and then paste it in. Okay, and what is the value of the flag that you receive when you successfully authenticate to the HQ admin portal? So if we know that the username is this and the password is this, then we can go to we can use Firefox and go back to our login page and supply all of the relevant fields. So we paste in our password, and then we solve the CAPTCHA ourselves. This one is 5329, okay, and then we click sign in. And then we receive the flag, which is this right here. We can copy it. And then we will paste it in. All right, so if you enjoyed this room, check out our red teaming learning path. So we can just click on this to complete it. All right, so we've learned a lot about machine learning over the last 3 days. I will admit that I don't know very much about machine learning, but going through these last few days, I feel that I've learned at least a little bit about how machine learning works. But I hope everybody learned a lot during today's challenge. But that's it for today. We'll be back tomorrow with the next Advent of Cyber 2023 Beginner-Friendly Security Cybersecurity Challenge. This is the Shy Hat, and we will see you next time.